Not all these words.
No.
You take every second word.
Oh,
Average and properties, open, closed, polygonal.
that would
How
about
about
do it.
Okay, that's the title of the talk Ken is about to give us.
Good. Thank you very much, Keith, for the
We're very
introduction.
glad to have had Ken. Incidentally, I should say that I first met him here. You were here in the first opening program of the Newton Institute, I think.
Yes,
on
I
knots.
was. And when was that?
1991 or 2, around that period. And there
I
were
thought
two-
I met you first in Santa Barbara.
Well, yeah, you're right. That was before the Newton Institute
Yes,
program, just before it.
yes. just
One
before.
year.
One year before.
One year
One
before.
year.
Yeah, we ran a program,
Santa
that's
Barbara
right. So
was
that's where it was.
1991.
Yes,
And then you came for the knots.
That's correct.
Raymond Licorice organised here,
yes.
in parallel with one that we ran on Dynamo Theatre, the two programs. So since then, Ken has been, I'd say, a colleague from a distance. So
This is, thank you,
welcome
Keith.
back.
Thank you very much. And thank you for joining us this morning. This was the title of the talk I was thinking of giving some time ago. And of course, it's transformed itself a bit in the course of time. But the subject is very much the same. I'm interested in knotted configurations in 3-space. And in particular, I'm going to talk about knots in the cubic lattice, models for that, and in 3-space. And these knots, I call them polygonal knots or polygonal chains because they're made up of Oh, my screen went to sleep. I see, thank you. A little knowledge helps. There we go. Made up of straight line segments. And these straight line segments will all be of equal length, thus the equilateral. That's true. Part of the lecture will be on the lattice, and then we'll get a little more adventuresome and be off the lattice. And so the plan is to talk about things both on the lattice and in 3-space. I'm interested in some of the basic topological properties and also geometric properties. I'll recall some of the old theorems about the occurrence of knotting in such configurations. Talk a bit about how we go about trying to estimate these quantities using sort of random sampling, Markov chain sampling, and focus on actually proving some theorems or outlining the proofs of some theorems about how you can go about randomly sampling examples of these. So today I'm going to give you a little data, but not much, and mostly talk about how to prove a few things. So we're interested in things such as end-to-end distance. So that's if I have an open chain, I'm going to sort of begin my chain at the origin in 3-space and ask myself then about the probability distribution of the distance or the magnitude of the end, the terminal end, sort of the end-to-end distance, and how that grows or how that behaves as a function of the length, the number of steps in my polygon or random walk. Radius of gyration is another measure of sort of size. Of course, I'm interested in knots and interested in conformations or chains or configurations which are knotted, but also then, as I mentioned in our talk in the conference a few weeks ago, where the knot actually occurs in the course of the chain, and in order to measure its size and shape. What does this really contribute to the sort of physical, if you wish, properties of the chain that are distinct from the sort of random kind of scaling? So first of all, then just a quick reminder how we go about talking about or identifying knots and chains. We look at subsegments, find the center of mass, take a very large sphere centered at that center of mass at the chain, and then randomly select points in that sphere, close them up to give me a closed chain, and then calculate my favorite knot polynomial, and then take the So when I do that, I use the Humphrey polynomial. We do that, we get a we get a histogram of various knot types, maybe sampling 100 times or 1,000 times, or in the case, I think when I was doing this, 10,000 times. And so this one, the dominant knot type is the trefoil. And so if we take the dominant knot type and we call that the knot, the knotting of that subsegment. So one of the things that Ben Sheldon and I did was and Akash Dubey also, to do this a lot of times just to see whether or not this was going to be a useful tool. And we discovered that for all practical purposes, this was a good way of distinguishing or deciding on a knot type. So even if we required that the knot identification be consistent 90% of the time in all of these closures, we were still at about 86% success in terms of identifying knot types. So that says 14% of the time it was below 90%. But if you wish to only use 50%, then only 4 cases out of 1,000 in the sample we did failed to achieve that standard. So it was a pretty good measure. So the conjecture back in the 60s was that with increasing length, the probability of knotting goes to 1. And so we would like to be able to sort of measure that, observe that, both in random walks or random configurations on a lattice, a very popular model for physical materials, and also off lattice, that is just in 3 space. So the theorem from roughly is 2000, 1998. I see I have a bit of, for those who know me, I have a problem with dyslexia. And so numbers often are right, but not necessarily in the order in which you read them. So if you have a question about that, it's okay to ask, because this was reading 1998 as well, I believe. Either that or they're both the same year. What I know for sure is they're both the same year. So the answer is yes, and there's a way of proving this, that the probability does indeed go to 1. And questions has been how fast, numerical simulations to try to test that. The key idea is that, and this is not the sort of model they used in their proof, but the key idea is that if you can tie a little configuration here in the lattice, which is very tight, so tight though, so that if this occurs, then it can never be disrupted by any further or any other part. It's tight, in other words, there's no way to get through there to untie it. And off lattice, the same kind of estimates, same kind of arguments prove the theorems in 3 space. So once a tight knot is tied, you can't untie it. So one could be looking for configurations of this sort. And
sorry, how do you define a tight knot on the cubic lattice?
It's that no matter, so if I continue the chain, and from either end or the other, I will still, it can never enter the sort of convex hull of this.
It can't, because
there's no space.
As close together as they can
right,
be. Yeah.
There's no space.
It's self-avoiding.
Right, this is self-avoiding. Yeah, all my walks are self-avoiding. Right, embedded. And then you have to stay on the lattice. So you can construct things like that. And I'll show you another one which is a little more complicated, maybe in the next slide. No. Okay, so, but soon. So this would be the open knot type. Now, you can have a part that is knotted, but that lies inside of a larger configuration that's unknotted. So imagine that I had left some space there. I could go on and then later come back and untie that knot. So if I untie the knot, then we call that a slip knot. So, I probably wish I'd ordered these slightly differently. Slip knots occur, in my experience, the first time I was really convinced it was something I wanted to think deeply about was when Todd Yates showed us that there were slip knots in protein structures. I thought, gosh, if they're there, they're going to be everywhere. And in fact, here's how one proves this. Here is a sort of an example of a slip-knotted structure, namely if I start here and go along until I get to here, then I'll have a trefoil knot. But if I go back through here and end up over here and close, then I'll have an unknot. And this is a tight slip-knotted trefoil. So the theorem basically from a derivative of a theorem of Keston is if you see these things and you can see them like 3 times, then with exponentially growing probability, you're going to see them everywhere. So as the length of a chain goes to infinity, you're going to see a slip-knotted trefoil or other kinds of slip knots with probability 1. So slip knots are everywhere as well. And 2010, that should be right. I went through the analysis of the Keston pattern theorem, the work of Yunan Diao, Nick Pippinger, and confirmed that those arguments, with some perhaps sneaky modifications along the way, were sufficient to show that the probability that a self-avoiding random walk or polygon in 3 space contains a slip knot goes to 1 as the length goes to infinity. Yeah.
So can you go back to the previous slide?
Sure.
So tight, I guess in your sense that you answered Keith, that would be, but it's not tight kind of in a rope length, since you sort of push that as through, but presumably you also get tight.
Well, it's tight in the sense of rope length because if you try to, so for this specific configuration, you can't expand it anymore. Once you expand it, it's going to fill up the space there. And it's tight in the sense that I used it before, is that there's no space now to go through and retie the knot.
So what I was going to ask is whether you also find with some positive probability smalls, like with something that's tighter, and that way you can push that little thing through, and that would slip it out, but where it's like a bite.
Another, you mean like the Gordian knot problem?
Yeah, but
Right.
when you see that with positive probability, it seems like it would be that much more.
Oh, I don't know. Anyway, that's another lecture. Yes, yes, sir.
Forgive me, I'm not really a mathematician, as Keith will agree. But to me, as a physicist, those statements look rather obvious and
Yes.
easily proved. Are the proofs elementary?
Once you understand them, they're elementary.
That's true of all mathematics.
Okay. So one way of saying this is the Keston pattern theorem is not so easy to prove, I think. And once you're off the lattice, then you have to work quite a bit harder, I think, to find conformations which occur with a certain probability that you can estimate, and then estimate the probability that you will ever enter into that region again in the course of your construction, and show then get those numbers right, so you can show that as the length goes to infinity, then these are going to occur with probability 1. And those are, for me, very technical arguments. If you're familiar with Rayleigh's random flight arguments, those probability distributions involve Bessel functions and lots of wonderful analysis. And for those of us who are more geometrically inclined, that's a bit of a challenge. So those are serious arguments, I think.
Thank you.
So an issue of what a physicist means by prove and a mathematician.
Yeah.
You asked that question just the other day.
Right. And so in some audiences, I would have to say a rigorous proof. Stu Whittington taught me that there's an important difference between a proof and a rigorous proof. And so I'm one of those rigorous proof folks, but I'd love to hang around with people who merely prove things.
I think all proofs should be rigorous. The others should be called a demonstration.
Demonstrations, yes. Okay, but anyway, so lest I wander off too badly and forget to prove a few things, then we're interested in arguments which are going to tell us that we can, by some algorithm, some process, sample our space in a way which is faithful to the probability distribution that's natural to that space. So that if we're in a discrete space, we might want to say that every possibility has the same probability of occurring, for example, a uniform probability, or in a geometric space it might be a little bit more challenging. So the key focus in the arguments will be this notion of ergodicity, which for all practical purposes is we're going to focus on showing that every conformation can be reached from any other conformation with non-zero probability. So I'm going to show you methods or algorithms which will transform any configuration to a standard one. And the standard configuration, let's say for a 500-step chain, could be a straight rod. Okay? So that's going to be where the focus of the argument is. An algorithm which is going to take any conformation using a small number of allowable steps and end up with a straight rod. That tells me I can get from any place to any other place because I'll just detour to the straight rod. Okay? And that'll be sufficient with a little statistics to show then that the sampling method is going to...
Are you going to tell us anything about the minimal number of steps to do that?
No.
Thank you.
No.
I'll go home.
All you need to know is it can be done. Okay, so just to review a few, because in fact when you try to do this, this is sort of how one might go at this. The naive method is for a random walk is you just sort of start and head off and hope to keep going long enough to end up with, I think in today's lecture, maybe 300 steps, 200 steps. And in fact, that will often work, but not always. There's also the sort of reptation method where you might start with a rod and then at one end randomly add on a piece and erase it at the tail. So reptation is meant to sort of model how people thought, somebody might have thought a snake moves. Snakes don't move this way, by the way. But anyway, that's called reptation. The pivot method actually is the one that works in the cubic lattice and also can work in 3 space. And we'll talk a bit about that. However, in the lattice, Madras and Sokol, well, they proved the pivot method was ergodic, and I'll sort of use that idea in an extension. But they also proved that if you only use local kinds of modifications, that's not ergodic. So you need, if you want to do some modifications, you need things which are not strictly local. They have to involve things that are happening here in conjunction with things happening over there. You can't sort of just do it here, okay? So I'm going to show you an extension of Reiter's method from 1990 that's going to have some nice properties that I want to take advantage of. So the naive method, as I mentioned, is just a growth method. In 2 dimensions, you imagine you're going along this way, and then suddenly you're here, and once you're there, there's nowhere to go. That happens with positive probability, and so that makes this method unreliable. And so I've had students play around with this and try to tell me on average how far could they go before they ran into trouble, for example, a good sort of a little problem.
This happens in 3 dimensions.
Yes, yeah. Exactly. Right, I'm going to draw 2-dimensional pictures because it's easier for us to visualize. In 3 dimensions, it looks far too messy. But the principle is exactly the same. You basically build yourself a little cavity and you head inside and you can't get out. Okay? And so the reptation method, of course, as I described earlier, has problems as well. In particular, you can get trapped. And in fact, there are some conformations that you can't reach. In particular here, you're really stuck. There's nowhere to go. You can't, this is one of those unreachable conformations. And in 3 space, of course, you have the 3-dimensional analog of this. You're sort of stuck inside of a cube. And so, okay, that's a bit of a problem. You can actually do sort of estimates to count how often this can occur. So the pivot method, right. And I wish I had numbers on these. I have no idea where I am in this lecture, but anyway. The pivot method actually works quite well, and there the idea is you just find yourself a vertex in your conformation. So I picked, my random selection was this vertex, and then you take, imagine you're starting here, you take the tail, and you do a lattice symmetry. Okay, so this lattice symmetry apparently I chose here was to take this thing and rotate it counterclockwise 90 degrees. No, clockwise. Rotate it clockwise 90 degrees. So this conformation now becomes this little piece out here. So you take a random vertex, you take the tail it gives you, you take randomly a three-space, a lattice symmetry, apply it, and ask yourself, does the resulting conformation give you a self-avoiding walk? If the answer is yes, then you accept it. If the answer is no, you try again. And so in 1988, Madras and Sokol proved that this method is ergodic. Okay.
What does it mean?
It means that using this transformation, I can start from any conformation and do a sequence of these, now not randomly. You don't have to do it randomly. You can do it with cunning. I can start with any conformation, do a select a terminal in a symmetry, and then prove that ultimately I can get to the straight rod. Let me give you an idea of how I might go about doing this. Right. I have to think just a bit here. Oops, damn.
So the inverse, you can start with the solid rod, straight line, do these pivots.
And just go backwards and get anywhere you want.
Get anywhere you want.
Right. So here, let's just do it sort of simply. Suppose I was doing an induction on the length of the longest subsegment that's straight. And I see along here it's like 3, but I would really like to have 5. Well, I take this vertex and I do a clockwise rotation of 90 degrees, and suddenly now it goes straight out here. And now I have 5, and I just keep unfolding it that way. Now the reason I know I can do this is I can look at the convex hull of this configuration, and I know I'm going to have some segments on the boundary, and I'm going to flip them out. That's the basic idea.
Does it make sense to ask what is the probability of getting through a particular configuration? Because this might also depend on the method of constructing these things, right?
What is the probability of...
You are constructing a random walk in the space of these configurations, but as a result, some of these configurations might have a larger probability of...
Right. You have to do more.
Random walk.
You have to worry about something called detailed balance. That is, you have to balance an operation and its inverse, and then prove a statistical theorem that says that asymptotically each state is equally likely.
Okay, but you may prove things like like this for this.
Yeah, this is simply existence, that there does exist a way to start at the straight rod and go anywhere you want, or go from one place to any other place by some sequence. Then you have to worry about the sequence of operations and the probability, and so on. So you have to worry a bit about the algorithm. And this is absolutely a wonderful paper. Madras and Sokol's paper is a wonderful paper, I think. But as I mentioned, in '87, just the year before they published this paper, they proved that local moves weren't sufficient, that you had to do big sort of global moves somehow. And so in order to overcome that and to try to, in my mind, model things that correspond to physical motions. So imagine now I have this sort of thing and it's in a heated environment and they're sort of randomly vibrating a little bit. I'd like to be able to just use physical motions, big, flip things out of the configuration to model this process. Well, so here are some examples of this sort. For example, I might start with a little configuration like this and take these two edges and sort of, instead of going this way around, go up and over. Okay? So small movements of that sort. So there are a small number of such movements that you could do in the plane, and similarly in 3 dimensions. And Ryder proved that these kinds of movements, where I basically would say I can take in my chain a little bump like that and either remove it and push out at the end, or create it and pull back in. Okay, so in other words, imagine fixed length. I've got a bump over here, I sort of push down on that, that's going to cause everything to move along, and at the end I'm going to have to add on 2 pieces, 2 steps. Or I find a place where I can actually create a bump, So I pull it back in, create that little bump, and pull in the end. Okay? So
shifting along is permitted.
Shifting along is permitted.
Pivoting.
Yeah, in the picture, of course, nothing happens, but thinking about materials, you're sort of sliding it along. It's sort of like the snake or the worm, sort of stretching and retracting. So that be
But I
permitted.
thought you said before that's only pivoting.
So this is a new method. The pivots are big movements. Now these are smaller movements, but they're not, and like the pivot method, it's not local, because I'm going to do something, let's say do something here, and it's going to have an effect here and an effect there. So they're sort of bi-local. Okay? Now, unfortunately, in Ryder's method, he allowed, the question about implementation is key. Do you allow yourself to move into space before it's been vacated, sort of in anticipation? So let me see, I drew myself a little picture here to show you what I meant. Right, I start with a configuration sort of looks like this. Right, like that. Okay, now, and I want to end up with configuration that looks like this. Okay, something like that, and like this. Okay? So the point is, I have a bump here and I'm here. I'd like to bring this end down and move it along there. So basically, what I'm saying is, I don't like that movement, because that sort of imagines that I've somehow squashed this out in order to free up the space for this to move into. Right? The rule that I would like to require is, if you're going to stretch out the end, you have to have the space available to move into before you try to do the move. You can't sort of somehow imagine this erases, gets propelled along here, and then you move in. I want the space open before. So if you do that, I don't know what I have done here with my computer. So if you do that, you change your algorithm a little bit so it's a little bit more sort of spatially respective, then you can show, in fact, that this is an ergodic movement. So let's see. Also, you don't need reptation moves, okay? So let me see if I can show you how to prove this. Okay, so this is what I call an inchworm move, because this is sort of how inchworms move, and this is a picture of an inchworm. And so here's the idea. Right. So here, so right in, let me see now. Right here, I'm going to create a little bump. Okay, so I see these two spaces down here are available. I can then add on two edges, create this little bump down here. That requires at the end, I erase two edges. Right? So that's one move. The inverse is also possible, namely here, I want to remove this edge. I see, of course, there's nothing in there, so there's no problem here. But I check out here and I see, okay, I have two spaces available, so I can draw this in and move this out simultaneously. So that's sort of how inchworms move.
So the rule is that you can add any...
You can add anything at the end, so long as the space is available.
Yeah.
Okay?
Okay.
And so you can put in a little bump any place you want, so long as the space is available and contract. All right. So I claim that inchworms, in fact, do mimic physical movements. Well, in fact, and they're ergodic. And the proof that they're ergodic doesn't depend on the dimension. You choose your dimension. So the idea is something like this: take in three space a cube, but just take the rectangular hull, if you wish, of your configuration. On the boundary of that hull, then you can have no more than two vertices, because there are only two ends. So you must have some edges. And so if you have an edge, let's see here. So right out here I have an edge, I guess. What did I do? Okay, if that's right. So out here I have an edge. So what I can do now is right here add a bump. Okay? So if I add a bump, it pushes out along this edge, straightens this out, and gives me a larger rectangle and a larger interior piece. And I can try to do this again and straighten this out. So because there are always edges on the boundary of the sort of the box, I can now do the same thing here. I can start here, for example, or here, push out a bump, pull this thing back in, and straighten this piece out. Okay? So just a sequence of those operations will then ultimately give you a straight configuration, and that kind of argument works sort of in all dimensions.
But hang on, now
Yeah.
you're making the rectangle smaller on the other side. You have
Right.
to-
So it's what. So I didn't tell you exactly what the inductive criteria is, but you might think it's sort of like. So the inductive criteria here that I might be thinking of is I want to make the end of the tail as straight end of the tail as long as possible. Okay, so along here I have this, and now I'm going to do, say, a sequence of things here which will incorporate all of this into a longer, straighter tail. So that's maybe one way to do this.
But in the middle, the tail stays the same size, so there's some long plateau before you make
Right,
it
before I
progress.
make an inductive step. Yeah. So you got to be a little careful with your induction. Right.
Okay.
But basically, you would need a measure of getting closer to a straight rod. Okay. But this strategy of looking at the hypercube in whatever dimension you are in, with the argument that on the faces of the hypercube you can have there are only two termini, then says there must be edges, and then you can use those edges to straighten things out. That's the idea. Okay, so. I was hoping, so in lieu of having a movie, which I may or may not have, here is a picture of an inchworm starting from being really straight and doing 5,000 steps. And then another 5,000, another 5,000, another 5,000, and so on. And maybe even one more. So I show you these just to point out that even though these movements are very physical and random, there's a long history. So we can sort of imagine or see in here, well, this is still pretty much like a straight rod, it's just wiggled a little bit. And even down here, one sees, it may be just the way Mathematica organizes the image, but you still see a bit of the evidence of its history. And still here. So one of the key questions is, how long do you have to wait before an inchworm ties itself into a knot? How long does it take before the configuration you have is independent of the configuration you started with? Okay, and now in this, the pivot method is like, how to say it, it's an n squared. The answer is n squared. Inchworms are about n cubed. Okay, so this is not a fast kind of process if you're interested in sampling the space of configurations, but if you want to study things which are more dynamical, that is, you want to imagine this thing sort of moving and ask yourself, well then how long does it take to tie itself in a knot, then this is the kind of process I would say you want to do. So I wanted to give you some rough estimates here. So we know for 22-step trefoil, there are about 3,328 distinct one of those. Those are the number of 24-step minimal length lattice trefoils. Okay? Well, combinatorists can tell us roughly how many different distinct 22-step self-avoiding walks there are, and there are 1.1 times 10 to the 15. That's a lot. So the likelihood of seeing this is pretty small, is the point. So another estimate from Reiter is that the autocorrelation time, roughly the amount of time you need before you get independence, is around 10 to the 2 times 10 to the 6th. So you have to expect to let this run a long time before you're going to see some knots. Another way to try to do this is to ask what this looks like if I constrain my conformation to sort of lie in a small region. So I could say I'm going to preferentially allow my inchworm to move if it sort of decreases on average the radius of gyration. Shoot. Okay. Coming back. Oh no. Yes, but if I, so with the first 200 step, if I'm decreasing the radius of gyration down, then I'm able to get some occurrence of knotting. And then how are these knots formed? Well, how to say it? Just thinking about it casually, you would expect the knots to get tied on the ends and to be short-lived. And so these are the number of steps with the persistence that I observed when I ran an experiment a few weeks ago. And on average, they exist about 34, 35 steps. That is 35 discrete motions. The ones are clearly, I would argue, being tied at the ends and disappearing. But the other ones get a bit larger. And exactly how much larger, that's part of the research. That's part of the project that I'm working on. Here I'm showing you what happens in 3 space as a function of the number of steps. So if you see, if I take a 3 space random walk, and I was looking for data on this, the knots are up here. About 40% of the time in a 3 space random walk, I'm going to see a knot. In lattices, you don't see knots at this size and anywhere near this probability. So a question is sort of why? There's a clock there, that's good. Okay, so 3 space random walks, there's much less structure, right? The step size is still 1, but I don't have to take steps that are either straight or at right angles. I can go off at any angle. So they can be much more compact. That's why you're going to see much more, I'd say much more knotting.
So you would say that the lattice is much more self-avoiding.
Exactly. The lattice is self-avoiding. Now, I want to show you a picture of what a lattice knot look like. These are the kinds of ones that I see. They're not small, they're large. That is, they're not small in the sense that they only involve like 25 segments. They seem to involve a whole lot of them. You used to see a little tail from the fact that it started a long time ago as part of a rod. So lattice knots tend to be larger than off-lattice knots, is the point of this. So in order to sort of try to capture or mimic the same kind of structure that you see in the lattice self-avoiding walks, off-lattice, you have to impose some sort of what they call excluded volume. That is, you have to imagine your walks have some thickness, that they sort of repel each other, that they can't get arbitrarily close. So
have you compared like a triangular lattice to a square lattice to see if there's...
I haven't. Right. But I know there are differences. The differences, the lattice people tell me the differences are not in the scaling, but in the factor, in the proportionality factor. Okay. So,
Not in the exponent.
pardon? But not in the exponent, right. So the key idea about thickness is, again, sort of excluded volume. You want to have material there that tends to push these things apart, and in the lattice you clearly have it just by virtue of that structure. So what we'd like to know is, as a function of the thickness then, what can you say about the averaged knotting or slip knotting? What can you say about the knots and so on, just as we studied for cases where there was no thickness involved. So, well, for closed polygons, this is a really tough problem. The naive method, I should say, when I talk about the naive method, it's this. I randomly sample the whole space of all possible configurations. For each configuration, I then calculate its thickness and put them into bins and then study what happens in each bin. What makes it, I'd say, impossible to use is because things that are of reasonable thickness turn out to be really hard to find, or small thickness, at least in things which are very long. So even though the naive method works well asymptotically, it's not sufficient to give us a good enough samples. And for example, if you try to do a thick random walk using just going one step at a time, roughly, I'm not sure, somewhere like 100 or 200, you always are running into obstructions. So this sort of naive growth method doesn't really work. You have to start with something which is of your step length, let's say 200, and transform it into something which is of 200 and what you want. So this is what my student Laura Zerbel is doing in her doctoral dissertation. These knots, she has an algorithm that I'm going to tell you about that is ergodic and which actually allows her to sample then 3-space random walks with specific thickness. So on the left, here is no excluded volume, and here the radii, the step size is always 1. Here the radii of the tube are at least 1/10, 2/10, 3/10, 4/10. You know if you make them long, big enough, it's just going to be pretty straight. Okay? So at some point, these things are going to get longer and longer. These are not to scale, by the way. They're just the way the images get scaled. But they tend to get longer and more spread out. And you can sort of see this, at least at the extremes here. So how do you go about...
Sorry, I missed that. You mean, when you say thickness, you mean you have ribbons or a tube?
Tube.
A tube.
This is all three-dimensional now.
No, but you could have a ribbon in 3 dimensions.
Yes, right. But here we're working with tubes. So for the tubes, there's a constraint on curvature, on the bending angle, because you don't want them to be pinched too much. And you have to worry about distal effects. This edge, this step has to be far enough away from this so that you can fill in at least the right distance between them. Okay? So how do we go about doing that? Or how does Laura go about doing this? The idea is to the same sort of idea that I was telling you before for the lattice, namely a series of operations that starts from any thick conformation of any thickness, call it tau, and which, when performed, will take you to the straight rod conformation, and no step will decrease the thickness. The steps will increase the thickness clearly because the rod has infinite thickness, right? So each step will essentially increase the thickness perhaps, but it will not decrease it. So you're staying, if you have a configuration of thickness tau, you're staying in the subset of walks of thickness no less than tau. Okay, hopefully this will be yes. So here's the sort of idea. You have your walk-in space, and of course you don't have you're not on the lattice, so you don't have a big hypercube or anything, but you can take the convex hull, and you know on the boundary of the convex hull you're going to have vertices and you may have edges. So if you have a vertex which is not a terminal vertex on the boundary of your convex hull, then what you can do is, so the method is going to be reflections. What you can do then is to take a plane meeting there at this one point and take the sort of terminal segment which is inside the convex hull and reflect it outside of the convex hull. And you can do this in a way that does not decrease the thickness. So one reflection. But that's not enough to do the job, it turns out. Right. So anyway, that was just a little bit bigger picture of this sort of reflection here. This doesn't change any of the geometry here internally. What you have to worry about is what happens here and what happens between distant segments here, and show that the distances are never decreased. So in sports, with football players, soccer players, there's the fake, and then the real professionals have at least a double fake, or what is it, Cristiano Ronaldo has at least 3 fakes or something, or whatever. Well, here you need a reflection, but you also need a double reflection. It turns out a double reflection, if you do this right, will then allow you to sort of complete the process. So the double reflection starts out basically in a situation where we have maybe one of the termini on the boundary, and we're in pretty good shape. Maybe the other terminus is on the boundary, and we have a diameter here, a purported diameter, and we want to make this longer. So what one does is you start at your terminus that's on the boundary, and you look along the diameter, and you find, let me see, I forget which one this is. So you find a local maximum. Okay, so imagine the height goes up this way. So you find, with regard to projection this way, you find a local maximum here. We're going to now want to sort of do a transformation that's going to involve the distance from here to here. Okay? So I mentioned that we want to do a double reflection. So what you do is you now go along the segment in between those two, and you find the vertex that's furthest away along this axis. So you find the minimum of this segment in terms of the distance along this axis. And now we're prepared to do this double reflection, which says, okay, first reflect in this. So the double reflection requires this following observation. The intermediate stage, you can't ask me to have it the same thickness. It's going to be, you're not going to see the movement. It's all one movement. Okay, one transformation. It's a double movement. So the first step is to then just do a reflection right here. So what does that, it has the property of what? Popping this minimum out here, but the terminus now gets reflected through that plane. So it could be interfering with something inside, right? So it was out here, happy and far away, everything was good, but now I'm taking this whole segment, doing a reflection which flips it in that plane. It gives me a configuration like this. But now I know that this point, which was the lowest point, is now a maximal point in that direction, so it's part of the convex hull. So now I can do a reflection there, and the end result of my double move then lengthens the diameter and gives me a conformation that's going to have thickness that's no smaller than the thickness I started with. So that's the trick. You do this double move out, and that does not decrease the thickness. So, right. So now we're on the way to getting close to a conformation where we're going to have a straight rod. We can imagine that we do this process and we end up with one with no maxima and minima. So no maxima and minima says this basically sort of wiggles on its way up. That's not straight. So we're going to use more reflections to straighten that out. So that's sort of the next idea, that you have something going sort of like upward here, and you're going to try to straighten that out using some reflections. So you do one reflection here, which is you sort of construct, is going to move this guy over to here to straighten it out in the same direction that this part is, right? You have this part straight, it has a direction, you have this little kink in there, so you're going to want to flip this over so it's pointing in the direction parallel to that one, and then, so you do that. Of course, that messes up your original thing, but unfortunately you have the double reflection move, and so you straighten that out. So straighten that out takes a double reflection move. Reflection moves tend to pop stuff out to the outside, but when you get them out and you're almost getting them sort of with the vertices on the termini on the exterior, you've got to straighten out what's in the middle, and that's where the double reflections come in, both to extend it and to straighten it out. So that's the theorem.
What if you have a degenerate case, like saddle point? So you want to have a maximum and minimum. A
flat edge?
Right.
You can just use either one of those vertices because it'll lie in the plane. Yeah, I think you'll be okay there. Right. Okay, so that's the method. And then what you do then in your, so that proves that this method, when you check your statistics, your detail balance and so on, that this method is ergodic, and then you implement it by taking random points, planes, and reflections. So that tends to fold stuff up. Okay? So what I show you here then is what you get when you implement this method for the various thicknesses here that I mentioned earlier. So those were the two theorems. One was a way, the inchworm theorem basically says, here's how you can explore the space of self-avoiding walks on the simple cubic lattice via a physically realizable process. That is, you have little worms and they can actually do this. They're not sort of flipping things through dimensions and sort of insensitive to the sort of local constraints. They're sort of crawling around. The bad news is, of course, it will take them forever to do that. So the applications are, my applications are looking at sort of the dynamical process and the sort of onset and shape and persistence, if you wish, of knotting and other local structures. The second theorem is a sort of double reflection strategy, which says that for random walks in 3 space, then you can sample those by a method which does not decrease thickness. So you can start with a straight rod, a threshold for thickness, do these reflections. If you are within the thickness that's allowed, you accept them. If you decrease, you don't. And this is an ergodic method saying that you're going to asymptotically uniformly sample the space of thick random walks. So, okay. I had hoped to have data to show you. I've had examples, but the data is not yet, I would say it's still in the oven. Being here in Cambridge, and as Keith mentioned, a home of knot theory, at least for me personally, this is where the Humphrey polynomial was born, not in this site, but over on Mill Lane, and where you have these wonderful gates here with the Kinoshita Kawasaka and the Conway knots. I wanted just to mention one thing that is probably known not to too many people, and that is that these knots are in fact the union of 2 slip-knotted trefoils each. And here is the picture that gives the proof. Being a newcomer to slipknot land, so if you, for example, cut here and look to the left, just follow this strand around and back, you will see you have a slip-knotted trefoil. And if you look to the right, just follow this loop around and back, you have another slip-knotted trefoil. So these 2 wonderful knots celebrated here in Cambridge are in fact the unions of 2 slip-knotted trefoils, which I thought was absolutely wonderful. So, thanks to my collaborators, Laura Zerbel. Alex Lynn is an undergraduate at Santa Barbara who knows no fear, and who's working with me on the lattice simulations and so on. And of course, Eric and Akash and Andre were part of and are continue to be part of my collaborators on, well, Akash has gone on to other things, but Eric and Andre still hang out with me and worry about knots in lots of stuff, particularly proteins these days. Thank you to the Isaac Newton Institute for Mathematical Sciences and to this wonderful program that's just allowed me to have an absolutely splendid visit, both intellectually, mathematically, but in terms of the weather. And thank you for your patience and attention.
Thank you. Yes?
Yes, sir.
So you have an algorithm which works out how many knots you have in a given path, and whether these knots are slip knots or tight knots. How do you do that?
I wish I could say that we do it with real cunning, but in fact it's just brute force. And we'd sort of do it in the obvious way, namely, I have just as we did with the protein structures. We look at all subsegments, all of them, and we calculate their knot type using this random this closure to a sphere and the statistics of the closures to the sphere. So it's a very computationally intensive argument. And then we just look at all possible subsegments and identify what's happening there. So for example, to find a slip knot, what do? If I'm a chicken, which I usually am, I look at big configurations and I say, what kind of a knot type? If it's unknotted, then I say, okay, if there's a knot inside of it someplace, then for sure it's a slip knot because the big thing is unknotted. So then I start looking, I do a bottom-up search, shorter segments, longer, till I find a knot. Once I found a knot, then I go longer, till I find that it's unknotted. That gives me an estimate of the size of the knot in that location and the size of the unknotting portion. And then I check the complements to see if there were, because it's possible I have a, quote, God forbid, connected sum of slip knots. So slip knot, this can, well, anyway. So this is like a first level, a coarse grain analysis. That's what I actually do.
So it's a very long time to check that.
Yes. So for example, this data I showed you with the inchworms, I optimistically started it a little earlier this week and had hoped to be able to show you a movie picture of a slipworm tying itself into a knot. So what do? I say, slipworm, move. It moves. I say, are you knotted? No. Okay, move again. And right now we're up to about 80,000 moves. Still no knots. I haven't told it to crunch up, right? So it's still doing its sort of average radius of gyration. Anyway, so that's what I do. I just say, move. Are you knotted? No. Okay, move again. And Alex is working on trying to be more cunning than I am. This fellow, he's a sort of double major in math and physics at Santa Barbara, and a person who's, I met him when he was a sophomore, and I gave him this paper of Madras and Sokol and said, read this and tell me what you think. And he did. I said, I couldn't believe my eyes.
So you're hoping that some kind of invariance can be calculated?
Here's my actual hope is, so when I was a kid, there was a game called Battleship, where we had little things and then a blind board, and you would drop depth charges, or submarine maybe it was called, who knows. But you're randomly going to guess in this sort of thing and try to identify where something is. Well, I think here what I'm hoping is that we can come up with a more intelligent procedure about how to localize where to look for the knot. And maybe a coarse grained look, and then a finer grained look, and some statistics. That's what we're trying. It's just, how to say, it's Keplerian mathematics, right? You collect all the data, you look for the patterns, and then you try to figure out what it's telling you. And so that's sort of where we are at the moment in that strategy. Other questions here?
So I'm kind of concerned about detailed balance.
Yeah.
So with the inchworm, right, on the lattice walks, for instance, it seems to me that if the algorithm is like, generate a kink and delete stuff from the ends, or delete a kink and add stuff to the ends or something, then to say that those two are equally probable, you have to say how I'm selecting which potential kink to generate from all the potential kinks on your initial and terminal configurations.
Right.
Right, well, how do I know that they're the same number of potential kinks? Because if by generating a kink, I open up 20 new kinks that I previously didn't have in my other configuration, then the probability of going back is not the same as the probability of going forward. It's less because there are more options to choose from.
I think I have to sit down and think about that. What we do is very, I think, close to what you're saying, but I'm not sure it's exactly what you're saying. We don't, I would say, we don't, so where these kinks, where these little bumps can occur,
Right.
or there's another aspect to this that I'm not coming up with right at the moment. Whether the other right. So here's the deal. So either you've got to find a place where you can make a bump and shorten the end, or you're going to find a place where a bump exists and you're going to eliminate it and elongate the end.
Right.
Okay. So there's the shrinking and the two processes. They're not equally likely. So the detailed balance required an analysis that tells me which of these operations I'm going to select with what frequency and a little bit more.
It seems very non-trivial then, because knowing the probability that you're going to select
Right.
things by seems to be a serious calculation.
Yep. Well, so and it's a demonstration.
Okay. It's a demonstration. It's a demonstration of detailed balance.
Right. It's a demonstration of the detailed balance. And
Alright.
here's how we demonstrate it.
Mhm.
The way people in this field do it in general, and that is we run the data, we then look at the scaling of the radius of gyration and end-to-end distance. We have the exact numbers up to about 36 steps. I think the combinatorialists can tell us exactly how many configurations there are, exactly what the total radius of gyration is. We divide and we see whether we get the right answer. And so that's the state of the art in that field.
But your conversions rates, you already told us, are very slow.
Right.
Lots and lots of steps.
Right. Well, so it becomes offensive when you're trying to do 200 steps, but when you're trying to do 36, it's not so bad. Yeah. And I'm really interested in more like 200, 300, 400, 500. And so we work really hard on the shorter ones to make sure that the method is giving the right convergence there. And it's not a theorem, it's a demonstration that it's giving the right convergence there, and then we hope that life continues continuously.
So I want to ask, a little follow-up to that. And so your objection was that there's asymmetry in going one or the other way, but you need to have it exactly just up to a certain constant. But that's one thing. But
Yeah,
that's just
and I think you're right, Rob.
But I've got a different question that I should ask, and it's more open, more Ptolemaic. So, Andres was saying that ultimately what you'd like to have is something akin to, say, the Conway, or maybe it goes back to earlier presentation of two bridge knots as rational tangles, where you look at decompose in little pieces, and double helix twists one way or the other way in the Conway picture. But in your picture, you've got the two examples of the gates. You've got this way of decompose, sort of primitive factors, not like a prime decomposition, but primitive factors. And that's what I really wanted to ask is whether, because you've been in the business for a long time, whether that seems like a promising thing or just pipe dream.
So
I think it was like a complicated knot, just sort of, you always have to find sort of primitive pieces.
That's I think so. I think that's a wonderful question, and I don't know how to attack it. But here's the idea. So what I first noticed is in the classical knot diagrams, I could identify subknots which sort of like irreducible knotting. So like indivisible or irreducible knotting, like the atomic particles, right? The elementary particles. And so the question was, well, what are those elementary particles out of which you can build any knot? And so you look first and you see, like most everyone, you see lots of triploids. But then you see some figure eights. And the question I would have is, are there only finitely many of these sort of irreducible or elementary knots, out of which every knot is constructed first? And so that might be ideal knots, or some fixed for it. But now you say, well, let's suppose we take your random Kinoshita Kanwei Terasaka nut, or Kinoshita Terasaka or Kanwei nut. Take any one of those. Will I always be able to find within them slip-knotted trefoils? Okay, to the extent to which these sort of very irreducible basic knots are present in there, that's not so clear over the rand. You can put any knot type you want. Here's a theorem. In any knotted polygon, so suppose we think about knotted trefoils. With probability 1, as the length of your knotted trefoil increases, you will see inside of it a slip-knotted figure-8 knot. Okay? What I can't say is, if you take long unknots, will I see a slip-knotted trefoil or slip-knotted figure-8? I can't say anything about asymptotic presence of knots in trivial knots, but you can see lots of noise inside of any knot type. It's certainly true that you will see slip-knotted trefoils inside of unknots. No one knows how to prove that. Not only I, but nobody knows how to prove that kind of thing. So there will be lots of noise in there, is the point. But will there always be in the Conway knot, you will always see trefoils, or slip-knotted trefoils? That is maybe a pipe dream, or maybe an interesting problem. But we don't know that kind of thing about knots. And I think we've never actually studied it, because those kinds of questions, at least as far as I can see, aren't topological questions. I don't know how to translate the fact that inside of most every knot I see a trefoil into anything that I can get my hands on that's topological. So, anyway. Yeah, I like that question a lot. But I don't have anything other than enthusiasm to contribute.
Well, I think the time has come for us
Probably.
to make a polygonal walk to lunch.
Yes, I agree. Thank you, Pete.
So thank you again.